Hey everyone, so we're on to the next force when it comes to the special forces, and we're going to talk a little bit about circular motion. Again, this is another one that is very clear cut when you're going to be using this. So we've done linear motion stuff, we've done two-dimensional things such as projectiles. We're going to actually look at another two-dimensional motion, which is the circular motion. As the name implies, it's moving in a circle. Who would have guessed by the name? Now, one thing that we're going to be looking at is because circular motion can actually come in a variety of different forms. If you know anyone in the AP class, you might know that they end up doing what's called vertical circular motion. What we're actually going to focus on is the more basic form, where we have an object that's going to be moving around in a horizontal circle, much like the corgi, and it's going to be moving at a constant speed. A lot of times this is going to be called uniform circular motion. So you're going to see that name pop up. It just means that the object is moving in a horizontal circle rather than a vertical circle where the speed wouldn't be constant. All right. Now, the question is, since the speed is constant, would an object moving in a horizontal circle be considered to be moving in or be in equilibrium? Well, the answer is no. As we've said before, the statement for the definition of equilibrium is that an object has to be at rest or moving with a constant speed in a straight line. So, even though the speed is not changing, the direction is changing, or its velocity is changing. Therefore, there will actually have to be an acceleration. It seems weird to think about that the object is the speed's not changing, and normally the way that we consider acceleration, the way we tend to use it in our everyday lives, we think of acceleration being tied with speed, going faster, going slower, but direction does play a part in this. In order to actually turn something, there does have to be a force acting on an object. There does have to be an acceleration on that object. So it is important to remember that circular moving objects are always accelerating. Now, we would like to see what's the direction of this acceleration. And normally what you would do is you would have to look at the velocity. So if we look at this object, an object over here has a velocity that's going forward. Because remember, if we cut the string here, an object will continue moving in a straight line. So it will no longer be in the circle, it will move tangent to the circle. When it gets to this point, it will once again move tangent in a straight line. The fact that the velocity starts going upwards and then ends up going downwards means that the acceleration has to be pulling it down in order for it to go going up to then coming back down, uh, much like a projectile. It turns out that the acceleration will actually always be towards the center. So this is actually very important to remember because one of the questions that they love to do is they love to have diagrams given to you, and you have to figure out what direction the velocity is. The velocity is always tangent, again because of Newton's first law. Objects moving with a constant velocity will continue moving in a straight line within balanced forces. You can actually see it in this little animation that when the guy does fall out of the circle, he does in fact move in a straight line. And like I said, the acceleration is always going to be pointed towards the center. So in fact, as an object moves in a circle, you'll see, as this animation shows, the velocity and the acceleration are always going to end up being perpendicular to each other, forming like an L shape. If they don't form this L shape, they are not going to be in a circle, or they're not going to be in a uniform circle. They may end up creating an elliptical path or a spiral path if they weren't at a complete right angle. So in this class, because we're always going to be doing this uniform circular motion, they will always be perpendicular to each other. Now, because the acceleration is pointed towards the center, we actually call this a centripetal acceleration because centripetal actually means center seeking. It goes towards the center. And like I said, velocity is always tangent to the circle and is always perpendicular with the acceleration. Now there's an equation to figure out the centripetal acceleration. It's given on the reference table as AC equals v squared over r. So AC is your centripetal acceleration measured in the same units of meters per second squared. V is your speed or your velocity. Meters per second is the unit for that one. And then r is going to be the radius of the circular motion. So whatever the distance is from the center, that's going to be plugged in for r. R has to be measured in meters in order for all these units to actually make sense. All right. So here's the first question. Pause the video, work itself, and we'll go over in a second. All right, so when we go reading through this question, we write down everything that's given to us. They tell us that the mass is 5 kilograms, the speed is 6 meters per second, and the radius is going to be 2 meters. We don't have to do anything else with those numbers. They want to know what the acceleration is. So because it's a circle, we know that it has to be using the AC equation. AC equals v squared over r. One thing to note, this little subscript, again, stands for centripetal acceleration. You can remember it as being representing circles. So when you see the word circle somewhere, you know you have to have a little C subscript. So plugging the 6 and the 2 into the equation, the mass actually plays no part. We end up getting that the centripetal acceleration is 18 meters per second squared. Okay. Now, because there's an acceleration, we know by Newton's first and second law that there also has to be a net force. And wouldn't you guess it, we call this net force the centripetal force. So we have a centripetal acceleration and a centripetal force. And based off its name, I bet you can guess that it also goes towards the center. So both the acceleration and the force go towards the center. I've said this before, but net force and acceleration are always pointed in the same direction. There will never, ever be a case where the acceleration and the net force do not point in the same direction. Now, one thing that I want to point out is there is a thing that I want to clarify. Now, I've been calling the centripetal force a net force. That's because there is no such thing as a centripetal force in the sense of there being like a normal force or a gravitational force or tension force or frictional force. The centripetal force is the sum of all the forces that are actually causing the object to move in a circle. So there is no such thing as a centripetal force, but forces are acting centripetally. So those forces that we've talked about, gravitational force, normal force, tension force, those will end up being the centripetal force. Now, the reason I point this out is because when you do questions in this topic, a lot of times they're not going to come straight out and say, hey, what's the centripetal force? Instead, they're going to say, what's the tension force? And you have to realize that by reading the question and looking at the context clues, that the tension force is the centripetal force. So again, it's that big thing. That's the one thing that people need to get a handle on in order to do a lot of these Regents questions, is to realize how to mix and replace words into the question so that you can understand what it's actually asking about. Now, one of the big questions is the force is always pulling us inward, but the thing is, we always feel ourselves being moving backwards. If you've ever been on the Gravitron at a carnival, you know that when the ride starts turning, you start getting pushed backwards up against the wall. But again, there is no force pushing us backwards. There's only a force pulling us inward. So one of the questions is, well, why do we feel like we're going backwards? Again, we're not actually moving backwards. What we actually want to do is move in a straight line, tangent to the circle. But we can't move tangent to the circle because we have something keeping us there. In the case of the gravitron, the wall, which is actually blocking our path and having to push us in order to keep us moving in a circle. So while it seems like we're being pushed backwards, we are actually just moving tangent to the circle at all times with a force constantly pulling us inward in order to correct our motion to keep us in the circle. Now, the strength of the centripetal force is given by the equation Fc equals mac. Now, this is on the reference table. However, this equation, the way it's written, is not useful. Instead, what we are going to want to use is combine the AC equation that we got before with this Fc equals mac equation to get mv squared over r. Again, it's just taking the two equations and plopping them together. This is not on the reference table, so it's just very useful to remember it. But again, you could just take the two equations, they're right next to each other, and plug them into each other. This just kind of goes back to the same idea. There is no such thing as a centrifugal force. Depending on who you talk to, they might actually say differently. It depends on the reference frame. I'm not going to go into that too much. But the whole idea is that it's a force that we feel, but it doesn't actually exist. Kind of how if you're in an elevator that starts going upwards, you'll start to feel yourself being pulled downwards. However, the actual forces on us are actually going upwards. All right, so in this question, what you're going to do is there's in here there's two scenarios. I want you to figure out what force is acting as a centripetal force in these two cases. So in the first case, it's going to be the bolo, and then second case, it's the half pipe. So pause the video, works itself, and we'll go over in a second. All right, so in this first case with the bolo, again, the centripetal force is going to be one of those other forces that we talked about: tension, normal, gravity, friction. In here, it's very clear that the bolo is being connected by a string, so that's a tension force. If you cut the string and you get rid of the tension force, that object can no longer stay in the circle. So tension force will end up being your centripetal force. For here, the half pipe, so the thing that's keeping them in the circle is the surface. This surface is providing a normal force. So the normal force will end up being the thing that keeps them in the circle. So that is the centripetal force. All right, so here are the next three scenarios. Again, pause the video, work itself. Go over a second. All right, starting with, we'll start with this one. So while the people go on the track, again, the track is keeping them in the circle. Without the track, they wouldn't stay there. So the normal force that's keeping them in the circle is going to act as the centripetal force. Here, the satellite orbits the Earth. The thing that's keeping them in the circle is gravity. So the force of gravity will end up being the centripetal force. This one's a little bit trickier, but it turns out the thing that keeps these cars in the circle will actually end up being friction. This makes a lot more sense when we realize that if a person is turning in a circle, driving in their car, and they hit a patch of ice or an oil patch or something slippery, their car will no longer stay in the circle and they'll actually veer off to the side. So friction is actually the main factor that keeps objects moving in a circle in this scenario. So the frictional force will be the centripetal force. Again, the main reason why I'm going over this is because you're going to see questions with circular motion, and instead of saying, hey, what's the centripetal force they feel, they're going to say, what's the frictional force? And instead of going through the process of doing mu Fn, you should realize that you have to do centripetal force instead. All right, so here's the next question where we actually calculate stuff. Pause the video, work itself, and we'll go over in a second. All right, so going through everything that they give us, they tell us that the mass is 10 kilograms. We know that the force is 200 newtons, and we know that the radius is 80 centimeters. But because of the way our units work out, I need to make sure that I convert that to meters. So it's going to be move the decimal place twice to get 0.08 meters. They want to know what the speed is, so the only equation that relates them is Fc equals mv squared over r. Again, this is our altered form of the centripetal force equation. Plugging our numbers in, and solving for V, you should get 1.26 meters per second. So just to clarify, you would multiply the 0.08 over to here, divide by 10, and then square root. All right. The next question, pause the video, work itself, and we'll go over in a second. All right. So here, again, everything that we know that the velocity is 10 meters per second. We know its radius is 20 meters, and they're looking for the centripetal acceleration. So I go back to using that equation. I'm going to plug the numbers in, and I end up getting that the centripetal acceleration is 5 meters per second squared. All right. Question 15. Pause video, work stuff, and we'll go over in a second. So here, once again, going through everything that they tell us that the mass is 1,000 kilograms. We know that it's moving at 20 meters per second, and that we can experience a maximum frictional force of 8,000 newtons. Again, going back to here, they're asking about the frictional force. They don't say centripetal force, but because I know I'm moving in a circle, I know I have to use the mv squared over r equation, solving for r. So when I plug my numbers in, move some things around, do a little bit of algebra, I get 50 meters as my final answer. All right. Now, question 16 is a little bit different. So pause the video, work on itself, and we'll go over in a second. All right. So here, they want us to find the centripetal force acting on them. So once again, I'm just going to use the equation Fc equals mv squared over r. So we're not explicitly told what the mass is, but we can find that by getting rid of one of the zeros and making this 80 kilograms. So 80 times 5 squared over 5 gives us a centripetal force of 400 newtons. Now part B asks, well, what is the force that's actually acting as a centripetal force? If we think about what's keeping the runner in a circle, it's not connected by a rope, not touching a wall that's keeping them moving in a horizontal circle. There's no person pushing them in. There's no gravity pulling them in. It's the only thing that's acting on them is friction. So it's the frictional force that's acting as the centripetal force. And then part C, what could happen to him if the radius is suddenly decreased? The main thing is that he would slip and fall and no longer maintain that circular motion. Basically, if the radius decreases, according to this equation, then the centripetal force becomes really big, meaning that it may exceed the amount of friction that the ground can actually hold on to you. If you exceed that frictional force, you'll end up sliding and falling. Now, circular motion is a very important aspect to life. In fact, it has so many different purposes. Mainly, one of the great things about circular motion is that it's a really easy way for us to get very high accelerations in very small areas. If we didn't have circular motion and we just had to move things in a straight line, it would take a lot of energy and a lot of time in order to accelerate objects to very high amounts. You may wonder, well, why would we want to do this? Well, things like putting blood into a centrifuge is extremely important to kind of separate the parts of the blood and do things like that requires very high accelerations. And in fact, also requires that for long periods of time. Another thing that works with circular motion are things like your washing machine and dryer. What they actually do is they'll move it in a very fast manner in order to have the water molecules actually rip away from the clothing. That's one of the reasons why you may notice that the dryer drum has these little holes in them, is so that water can actually go out outside of it away from the clothes. It's also used in high G training. So anyone who knows about pilot training knows that they typically have to be able to withstand very high accelerations. So this is a way for them to kind of train themselves so that they don't pass out. Because when you're flying a plane, the worst thing that you want to do is actually pass out due to the high G forces. I have some videos that you can try watching. I'll probably try showing it to the people in class. All right, so here's some other things. Now, the last thing that I want to do is talk about one very important thing that comes up not just in this topic, but in the next video I'll mention it again. It's called the 1-1 method. So a lot of times what you'll notice is that um, instead of giving you numbers to actually calculate stuff, what they'll instead do is tell you how they've changed certain variables in that equation, and they want to know how that affects things on the other end. So like they'll say that they changed the velocity, and they want to know how that would affect the force needed to keep it in a circle. The best way to do this is to use what I call the 1-1-1 method. Um, so this is a common example right here. How would the force change if the speed is doubled? So there's no real numbers, and they're not even really asking for real answers. So what I would recommend doing is using this in order to cut down on any actual math. Because if you didn't use the 1-1 method, what you'd have to do is make up a before scenario where you have a speed, a mass, a radius, figure out what the force is. Then you make up a new scenario where you have the speed value, whatever you chose, being doubled, and then recalculating everything and then comparing those answers. That's a lot of work. That's multiple steps for a multiple choice question that should only last less than a minute. So this makes the process significantly easier. So the steps for this, the first one is to read the question to figure out what's being changed and what isn't. You also want to figure out what equation you're going to be using. Are you going to be using the centripetal force equation or the centripetal acceleration equation? Then what you're going to do is write down the equation. Now, the important thing is, even if they do tell you numbers, you're not putting in any real numbers in these equations. All you're doing is looking at the variables, and you're going to plug in numbers that represent how they change. So you're going to end up plugging a 1 in for anything that stayed the same or remained unchanged. If they don't mention it in the question, then it didn't change. So everything that stayed the same becomes a 1, and any variable that was changed gets a number representing how it changed. If it got doubled, you put in a 2 because it increased by a factor of 2. You doubled it. You multiplied that number by 2. If it tripled, you multiply it by 3. So you put a number 3 in for that variable. All right. So going back to the scenario before, we had what would happen to the force if the speed is doubled. Well, the mass in the equation, it was Fc equals mv squared over r. The mass and the radius remain the same. I'm looking at what's happening to the force, and they tell me that the velocity is doubled. So I put in a 1 and a 1 for the m and r. The 2 goes in for v. I'm squaring it, and I get 4. What this tells me is not that the centripetal force is 4. It tells me that the centripetal force is quadrupled, multiplied by 4, increases by a factor of 4, however you want to say it. So if they gave us an original number, I can then multiply this by whatever the original force was to figure out what my new force is. It takes a while to get used to it, but it is a very straightforward method. And like I said, we're not going to be doing it just in this topic. We're going to do it again later on. So here's the first question. Pause the video, work itself. We'll go over in a second. All right, so this is exactly what I mentioned before. They tell us that we're looking at the centripetal force to keep it moving in a circle. We already went over this, so I'm not going to mention that, though I made a mistake here. This should be a 4. So this is 4 times the original. So it got quadrupled, is what you would say. Here's the next question. Pause the video where itself, and we'll go over in a second. All right, so based off of this, they're changing the radius by half, and they're talking about the acceleration. So I'm going to use the centripetal acceleration equation. It tells us that the velocity stays the same. So I know that up 1 is going to be plugged in for v, and 0.5 is going to be plugged in for r, since it got halved. When I plug this in and solve for a, I get 2. So the factor that it changes by is a factor of 2, meaning that it's going to end up doubling. So by halving the acceleration, halving the radius, we end up doubling the acceleration that a person can feel. If this loop-de-loop was already nearing the limits of human ability to withstand the centripetal acceleration, like about 5 Gs, this would double it to 10 Gs, and most people would probably pass out and maybe even die. So going to the next one, they want to know about, well, what if we kept the acceleration the same? How would you have to change the velocity so that the centripetal acceleration didn't change and these people didn't die? So now the 1 is going to be plugged in for A. We're going to keep the 0.5 in for R and solve for V, and we end up getting 0.707. Again, this doesn't mean the velocity is 0.707, but that the velocity is going to decrease by this factor. So if my original velocity was 100 meters per second, well, now my new velocity would end up being 100 times 0.707, or about 71 meters per second. So it ended up decreasing by this factor. And that's pretty much it. Like I said, we'll be doing a lot more practice with the 101 method. It's a little bit tricky at first, but again, you do get used to it after a few practice problems. And like I said, it does not stop in this topic. It gets brought up in pretty much every topic after this. So it's extremely important that you know how to use it. Again, if you have any questions, feel free to let me know. Message me or remind. Otherwise, I'll see you later. Good luck and have a great day.